All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. Glad you could be here with me today. We're continuing our discussion of Unit 6 on thermochemistry, and we're hitting topic 6.5, which is going to look at the energy changes that take place during a phase change, right? And so if you think about the last topic we looked at energy calculations when temperature is changing. So we looked at Q equals MC delta T. Well, we want to throw in there now, how do we calculate energy when the phase of an object, when it's going from a solid to a liquid or from a liquid to a gas, how can we calculate the energy during those changes? Because we're going to find that there's going to be a very important difference between how we do that. Now, this is going to correspond to section 11.4 in our Brown and LeMay textbook. So if you have that, please make sure you read it. I think it'll provide you with some insightful information. It'll give you an idea of what we're going to be looking at. So let's go ahead and take a look at this. Now, here are phase changes in energy, just even from a perspective of endothermic versus exothermic. And again, it's going to kind of, when you start to think about it, it's going to make sense, but initially, it's going to feel kind of weird, right? So everything that's in this diagram that's in blue is going to represent an endothermic process, right? So, and what we mean by that is energy is going to go into your object in order to cause this phase change to occur. So when something starts off as solid and it goes to a liquid, it's melting, or we sometimes call that fusion. Energy is going into it, so it goes to the liquid phase. And then from the liquid phase to the gas phase, we input more energy and it vaporizes. All right, so it vaporizes or it boils. And then the other piece is you could have sublimation, which is when you go from a solid directly to a gas. And again, we can see energy is going into it. It's going directly to that gas phase. On the flip side of that, going in the opposite direction, so starting as a gas and going to a liquid and solid, these are going to be exothermic processes, so something like condensation. Condensation is an exothermic process. Energy leaves whatever substance it is, moves into the surroundings, and then it becomes a liquid, right, for condensation. And then going from a liquid to a solid, when a liquid freezes, it's releasing energy, the liquid is losing energy, and it's becoming a solid state. Or when something goes from a gas directly to a solid through deposition, energy is released by the gas into the surroundings until it goes to that solid state. Hopefully that makes sense. Now, energy change and changes of state are unique here. So you're going to have these various heats of fusion, vaporization, and sublimation. And each of these is going to require the energy required to change to that particular state. So the heat of fusion is the energy required to change a solid at its melting point to a liquid. The heat of vaporization, that's going to be the energy required to change a liquid at its boiling point to a gas. Now, this is important that we focus in on the boiling point. So we're at the temperature at which the substance boils. It converts over to a gas. And then lastly, the heat of sublimation is the energy required to change a solid directly to a gas. Now, if you're looking at our charts over here, in red, that's going to be your heat of fusions. In blue, those are your heat of vaporizations. And then in green, those are your heat of sublimations. Now, one thing that you should notice in all of these, whether we're dealing with something that's non-polar like butane, whether we're dealing with two polar substances like diethyl ether and water, or even if we're dealing with a metallic substance, we should notice is there's a pretty big jump from our heat of fusion to our heat of vaporization, right? And I want you to put this in the context of intermolecular forces. When you're going from a solid to a liquid at your heat of fusion, you're only breaking apart some of the interactions between your solid and liquid. But when you start talking about the heat of vaporization, you're talking about your liquid phase going into the gas phase. And if we tie that into intermolecular forces as well as kinetic molecular theory, for gases, we assume that there are no intermolecular forces. So essentially what we're doing in vaporization is we're breaking all of the intermolecular forces that are holding your substance together in that liquid state. And so that's why we see this very large jump from heat of fusion to heat of vaporization, because in heat of vaporization, we're breaking all of the intermolecular forces in that substance until everything has been converted into that particular phase. And then one last note on this slide, we can see that the heat of sublimation, the green bar, in all of these examples is essentially the sums of the heat of fusion and the heat of vaporization. That's a pretty routine way of looking at that. Okay. Now, that's going to lead us into heating curves, heating or cooling curves, whichever one that you want to use, right? Heating curve is obviously if you're heating the object. Cooling curve would be as if you're removing energy from the object. So this plot of temperature versus heat added is what's known as a heating curve. Okay, so notice heat added is on your x-axis, temperature is your y-axis variable. Now, on this graph, you can see you've got several sloped lines. You got A, B, C, D, and E, F. But then you also have some lines that have no slope at B, C, and D, E. So within a phase, so like its segments A, B, C, D, and E, F, what we have happening is that the temperature of that object is changing, right? And so for each of those segments, the energy calculation, Q, would be based off of Q equals MC delta T. So at AB, it would be Q equals the mass times the specific heat of ice times delta T, right? So that'd be its segment AB. For the liquid water at segment CD, it would be Q equals M, let's just say Cl for liquid water, times delta T. And then for our steam at segment EF, it would be Q equals mCg delta T. And the reason why I made the distinction between ice, liquid water, and gaseous water is because the specific heats of a solid, liquid, and gas are different within those different phases. So you would use the appropriate specific heat value during those particular changes. And so notice in each of those, there's a change of temperature, right? So that's why we're using Q equals mc delta T. However, at segments BC and DE, which are labeled in red on the graph to the right, notice that for those, there's no temperature change, okay? And so during phase changes, that presents a problem. We can't use Q equals mc delta T because delta T would be 0 and there'd be no heat being added, but we know that's not the case. Because what's going on is that energy is being added to break those intermolecular forces. And so at segments B, C, and D, E, we would calculate the heat differently. We use a different type of expression. And so for those phase changes, it would be the product of the mass of the substance times its heat of vaporization or its heat of fusion, depending on which one you're talking about. So segment BC, this would be Q equals the mass of the object times the heat of fusion. And then for our segment DE, it would be Q equals the mass of the object times HV, right? And so looking at that graph, we can still calculate the energy change without having to worry about the fact that there's no change in temperature, okay? So I hope that makes sense. And if we think about this, at BC, what we have changing, this is going to be potential energy, PE. And same thing at DE, potential energy is changing. But in our segments that are based on changes in temperature, the energy that's specifically changing here is kinetic energy, right? And that should make sense. Because remember, temperature is a measure of the average kinetic energy of the particles in your sample. So just kind of keep that in mind in terms of what energies are changing at those particular sections on your heating or cooling curve. Now, I jumped the gun a little bit, but so we should recognize what all these things are. So we can calculate energy, and we can calculate energy at phase changes. We've got Q equals M delta H or Q equals N delta H. Q is heat, M could be mass, N is moles, and then delta H would be your heat of whatever phase change it is. Or you could do it in terms of molar heat. So just depending on your units, you're going to plug in the appropriate variable. And again, those heats of fusion or heats of vaporization, those would be provided to you within the problem. Okay, so you don't have to memorize heat of fusions or molar heat of vaporizations, things like that. Okay. All right, so let's walk through how would we go through and do this if we were asked to do a heating curve problem. So we've got our heating curve here, and it says how much energy is needed to turn 39 grams of ice at negative 11 degrees Celsius to water at 23 degrees Celsius. Okay, now for me, the first thing I would want to do is I'd want to identify essentially what sections am I dealing with on my heating curve. So it tells me that I start off at ice. So I'm starting off, remember this is solid, CD is liquid, EF is gas. So I'm starting off as ice. So I'm starting off in segment AB. So this is my starting point. I'm at A. And then I'm going to go, it says to water at 23 degrees Celsius. So in terms of my curve, I'm going to have Q1, Q2, Q3. And this would be Q4 if we needed it, and Q5. So for us, we're going to need to use those three sections. So that gives us an idea of, even before we go through and solve this problem, we know that we're going to have to do three separate Q calculations. Now from that, we've got two that are going to be based on changes in temperature, and we're going to have one that's going to be based off of a phase change, which is useful. Now, when we go to solve this, we're going to have Q equals MC delta T. That's Q1. Q2 is going to be Q equals M delta H fusion. And Q3 is going to be MC delta T. Right? And so if that's the case, we would need the specific heats of ice water, of ice that's a solid. And so you have to give me a second. I'm having to turn to it so I can find it. Unfortunately, I don't have those numbers memorized. See, even I don't have those things memorized. But let's see here. We're told that the specific heat of ice is 2.09 joules per gram Kelvin. So then our mass be 39.0 grams times 2.09 joules per gram Kelvin times, all right, so our T final, we were at negative 11 degrees Celsius. We ended at, that's where we started, was at negative 11. To get to water means we got to go to 0 degrees Celsius. So we got to know something about the melting point of water. So 0 minus negative 11 is our calculation there. So from that, we've got 39 times 2.09 times 11. Oh, oops, not minus 39 times 2.09 times 11. So to two significant digits, that's going to be approximately 9.0 times 10 to the second joules. All right. Let's see here. Let's say that we're given the molar heat capacity, or the molar heat of fusion is 6.01 kilojoules per mole. That means we're going to need to convert the grams of water to moles. So we're going to have 39.0 grams divided by 18.02 grams. That's the molar mass of water. So we got 39 divided by 18.02. So we've got 2.16 moles of H2O times 6.02. Oh, excuse me, it's 6.01. Want to make sure we get the right values in there. 6.01 kilojoules per mole. So we combine those two terms. We got 2.16 times 6.01. That's going to give us roughly, to 3 sig figs, 13.0 kilojoules. And then for our last piece, we've got 39.0 grams times 4.18 joules per gram Kelvin times our change in temperature. It's going to be 23.0 degrees Celsius minus 0 degrees Celsius. So you got 39 times 4.18 times 23. And again, for this one, we're going to need 3 sig figs. And so that's going to be 3.75 times 10 to the third joules. And so then we're left with just combining all of those terms together. I would say convert the joules to kilojoules to just make that easier. So you'd have, what is that? 0.900 joules plus 13 kilojoules plus 13 kilojoules plus 3.75 kilojoules. So we've got a total, Q total in this case, it's going to be equal to 17.7 kilojoules of energy has to be added in order to heat ice at negative 11 degrees Celsius to water at 23 degrees Celsius. Okay. Feel free to watch me work that problem out again. If there's anything in this video you didn't catch, feel free to go back and watch it. Or if you have questions, you know how to find me. Post them on Google Classroom, shoot me an email, and let me know. Guys, thank you so much for joining me. I hope this was insightful, and I look forward to seeing you guys again soon. Take care.